everyone, we will be discussing about electric charge, electric field, electric flux, and laws related to it. First, we need to know about electric charge. To easily understand the electric charge, let us rub the balloon to the hair of Grizzlyn. We see that the balloon attracts Grizzlyn's hair with some mysterious force. Two balloons that have been rubbed on Christian's hair will strangely push it other way. This occurs because of electric charge, which is displayed by the rubbing together of these materials. The hair becomes positively charged and the balloons becomes negatively charged, which is terminology developed by Benjamin Franklin. Opposite charges will attract another, which is why your hair sticks to the balloon, and like charges repel, which is why the two balloons push each other away. This property of electric charge is carried by certain subatomic particles, which are protons, the positively charged, and electrons, which are negatively charged. Along with neutrons, these make up all the atoms in the universe.
As this happens, electrons, which are the essence of electricity, are easily transferable, and it is the transfer of electrons. In this case, from the hair to the balloon that generates electric charge in the previously neutral materials.
Each electron carries with it the fundamental charge, which is 1.6 times 10 raised to negative 9 coulombs. This magnitude is negative for electrons and positive for protons. All charges are multiplies of this amount, except for the quarks. That is to say, electron charge is quantized.
We can categorize substances by their ability to transfer electric charge. A substance that can easily transfer electric charge is a conductor, while a substance that does not transfer electric charge are insulator.
Opposite charges attract to one another because of the electric force. This is outlined in Coulomb's law, which states that the magnitude of the electric force between two objects is equal to the Coulomb constant, which is 9 times 10 raised to 9 nm squared over c squared, times the charge on one object, times the charge on the other, divided by the square of the distance between them.
This is essentially identical to the Newton's law of universal gravitation. The only difference is that electric force can be attractive or repulsive depending on the sign of the terms and the resulting sign of the force, while the gravity is always attractive. Coulomb's law tells us that the electric force between two objects increases as charge increases and decreases as the distance between them increases.
Any charged object will create an electric field around itself, and if another charged object enters this field, interaction will occur. The strength of an electric field is generated by the point charge is equal to the Coulomb's constant times the charge on the object produced in the field divided by the square of the distance between them and whatever it is actually acting on it.
One way we depict electric field is by drawing electric field lines which generally point towards negative charges and away from positive. This doesn't really exist, but they are a convenient way to analyze the direction of a field at any point in space, like the field produced by these two opposite charged particles, which we can call an electric dipole. The more densely packed the field lines are in a particular region, the greater the strength of the field. Lines like this can be especially useful if many particles are produced in the field.
Gas laws tell us that in nature there is such thing as positive electric charges and negative electric charges. And these electric charges can interact with one another without even touching each other through what is known as electric fields. Electric fields are directed away from positive charges and towards to negative charges. Gas laws also help us to relate the flow of electric fields through a given closed surface to the charges enclosed by this surface.
As an example, let's say you have a hollow cube, and in this cube, you place one positive electric charge. Let's also say you have a second cube, the same size as the previous one, and you place two positive electric charges. Clearly, the second cube has a greater amount of electric field going through it than the first. We call this flow of electron field flux.
Now, let's go to electric flux. Let's talk about what it is and how to calculate it. Imagine if you have a surface with the electric field out of the surface, and that surface has an area. The product of this perpendicular electric field is perpendicular to the surface. The product of the electric field times the area is equal to the electric flux. Phi is the angle between a normal line and electric field because the normal line and electric field are parallel to each other. The angle phi is equal to 0 and cosine 0 equals to 1. What if the electric field is not perpendicular to the surface? Let's draw the normal line as parallel to the surface. And let's say an electric field is at an angle. This is the angle phi. This is the angle theta. So phi is between the normal line and electric field vector. In this case, the electric flux is gonna be equal to EA cosine pi. The electric flux has its maximum value when this angle is 0. What happens if the electric field vector is parallel to the surface or perpendicular to a normal line? Let's say that the electric field vector is here. In this case, the angle between a normal line and electric field is 90. The electric flux is equal to EA cosine pi. Cosine 90 equals 0, so electric flux is 0 on this case.
A point charge has a magnitude of 8 times 10 raised to negative 6 coulomb. A second charge has a magnitude of negative 2.3 times 10 raised to negative 6 coulomb and is located 0.15 millimeter from the first charge. Determine the electrostatic force each charge exerts on the other. Given radius 0.15 millimeter, convert it to meter. 0. First charge 8 times 10 raised to negative 6 coulomb. Second charge negative 2.3 times 10 raised to negative 6 coulomb. Formula. F equals KQ1 Q2 over R squared. Solution. F equals the K equivalent of K is 9 times 10 raised to 9 nanometer squared over c squared. Substitute all the given. Q1 8 times 10 raised to negative 6 coulomb. Q2 negative 2.3 times 10 raised to negative 6 coulomb. R 0. Cancel. Therefore, the answer will become negative 736,000 Newton. Two 1,000 gram masses, each with a charge of 15 nanocoulomb, are placed 2.5 cm apart. Compare the gravitational force to the electric force between the two masses. Ignore the force of the Earth on the two masses. Given mass 1,000 gram and convert it to kilogram, became 1 kilogram. Charge 15 times 10 raised to negative 9 coulomb. Radius 2.5 centimeter and convert it to meter, 0.025 meter. The missing are electric charge, then the gravitational force. Formula: KQ1 Q2 over R squared. Then the gravitational, GM1 M2 over R squared. Solution: the equivalent of K is 9 times 10 raised to 9 nanometer squared over C squared. Then the Q1 and Q2 is the Q raised to negative 9 coulomb squared over 0.025 meter squared equals 3.24 times 10 raised to negative 3 Newton. Next, gravitational. 6.67 times 10 raised to negative 11 nanometer squared over kilogram squared. Then the M1 and M2, the two masses, 1 kilogram squared over 0.025 meter squared equals to 1.0672 times 10 raised to negative 7 Newton. Next, we will divide the electric charge to the gravitational force. The answer is 30.35 times 10 raised to 3.
Let's move to the next problem. If a test charge is moved to a location 5 times as far as its original location, how does the electric field change? So let's write R2 is equal to 5R1. E2 is equal to the missing one, which is blank E1. So E is equal to KQC over R squared. E1 is equal to KQC over R1 squared. And E2 is equal to KQC over R2 squared. So E2 is equal to KQC over R2, which is 5R1 squared. So E2 is equal to KQC 5 times 5, which is the square, 25 R1 squared. So here, KQC over R1 squared is equal to E1. So we're gonna write E2 is equal to E1 over 25, which will result to E2 is equal to 1 over 25 E1. So the answer here is 1 over 25.